Right, hello everybody. We're on to the next module, the next part of Module 1, Aircraft Performance. We're looking at calculations of two things today. It's very important when designing an aircraft to understand the changes that you make to the airframe, how they affect the aircraft range, which we define as how far it can fly, and also the aircraft endurance, which is a measure of how long the aircraft can stay in the air for. The way that we calculate these two quantities is by developing something called the Breguet range equation. And we calculate it slightly differently for the two broad classes of aircraft that we've already spoken about. So we spoke about propeller-driven aircraft as being power engines. And we spoke about pure turbojets as being thrust engines. So we're going to develop it separately for those two, and we're going to show the velocities that we should fly at for maximum range and maximum endurance for those two different classes of engines. So by the end of this lecture, you'll be able to develop those equations for the Breguet range equation for both range and endurance, and you'll also be able to do numerical questions for estimations of range. So before we speak about range and endurance, we should define those two things. Endurance, we've already said, is how long can the aircraft stay in the air for. That's sort of common sense how that works. Range is how the maximum distance that an aircraft can fly for, but we're going to define three further sub-definitions of range just to help us perform some analysis that's actually possible with the relationships we've developed. So the first range, which is how far we can fly for, is the safe range. The safe range is defined as the maximum possible distance between two airfields that an aircraft can fly for. Now this includes all of the calculations of takeoff, climb into cruise, and then landing with some fuel reserves as well. So it's a very detailed and involved calculation beyond what we're really covering in this course. After that, we then have a slightly more abstract version of range, which is the still air range. The still air range starts exactly the same. We take off, we climb to altitude, and then the aircraft flies until the point that all fuel is expended. And at that point, that defines the still air range, or SAR, of this aircraft. That's still a little bit too complex for this course because we're not looking at calculations of fuel in either takeoff or in climb. We're going to look at something called the gross still air range. So the gross still air range is if we determine that the aircraft starts cruise at a given altitude and then with a certain amount of fuel. It's then how far the aircraft can carry on flying for until all that fuel is expended. Now that might sound like it's a too abstract example of range, since obviously aircraft have to take off and they have to climb, but in general, the relationship between gross still air range and still air range is pretty easy to determine. So if we can do this simpler calculation, we'll be able to determine the effect upon the slightly more complex range definitions. So you might think that it's just a simple problem of working out the velocity we're traveling at and then working out the fuel burn and then effectively working out how much fuel we use during that time. That sort of distills the fundamental part of the problem. But what makes it more complex is that the aircraft takes off with a certain amount of fuel. And as that fuel is burned, the aircraft gets lighter. So appearing in all of the equations we've looked at so far, most of the equations we've looked at so far, notably the aircraft speed equation, the weight is a major part of determining aerodynamic parameters. So if the weight is changing during an aircraft cruise, then that then turns this into an integral exercise. We have to integrate for this changing weight during the flight. And fundamentally, the problem is distilled into this, what I said was the Breguet range equation. This was first developed for propeller aircraft. It was developed by someone else who wasn't actually Breguet, but we can use it to help us develop the gross still air range, and we can distill it down to the fundamental concept, which is the rate of the aircraft weight reduction is equal to the rate that the fuel is burned in terms of weight. So we're going to use that to develop these relationships, and we're going to do it slightly differently for turbojets and for propeller-powered aircraft. So let's move over to the whiteboard now. So for this problem, we need to define a means to quantify fuel consumption. So we're going to start out defining two parameters. CT is the thrust-specific fuel consumption. And then C is simply the specific fuel consumption. Now the units of these will depend upon which source you're looking at. It will either it will either explain these parameters in terms of a mass or a weight. We're going to determine them in terms of mass. So CT is for thrust engines. So that is the kilograms of fuel burned per newton of thrust per second of thrust produced. You can probably guess that C is therefore for power engines. So this is very similarly kilograms per watt per second. Now we've got to be a little bit careful with these parameters because they're not always defined in these units. These units tend to be, well, this one tends to be given in grams per kilonewton per second, and that's actually the same unit. So those two are equivalent, or you might see it being given in kilograms per kilonewton per hour, for example. So you've got to have a factor of 3600 in your units if you're looking there. And of course these could also be given in US customary units. So this would be pound of fuel per pound of thrust per hour, for example, or per second. So just be careful with the units that we use there to make sure that we are making things consistent. So with these parameters defined, we can start to look at the Breguet range equation. So remembering our fundamental tenet is that the rate of the aircraft weight reduction is equal to the rate of aircraft fuel burn. I can't seem to be moving around the screen, so let's go over there. Okay, so the first one we're looking at is let's say the rate of aircraft weight reduction. So we'll call that dW by dt. And that's equal to the rate of fuel burn. So this has to be a negative. So if we develop this for thrust engines first, it's going to be minus CT, that's the thrust specific fuel consumption, multiplied by the thrust that's actually being produced. And so this is going to give us a mass, so we need to turn it into a weight. So we multiply by G. Acceleration due to gravity, 9.80665. So we can rearrange this equation, and we're going to end up rearranging to dt is equal to minus 1 over CT multiplied by T G dW. Now this turns it into an equation that we can end up integrating to get our endurance. Before we do that, we want to make something on this right hand side include the weight, because at the moment if we integrate this we've got no idea how it relates to the weight of the aircraft. So we do a little trick here. We say, well, the thrust is on its own, but we could make this equal to the thrust multiplied by the weight divided by the lift. Now those two are actually in the same units, so sorry, the same quantity, because remember that weight is equal to lift, so this is therefore equal to 1. So then we could therefore say that for our problem, remembering that thrust is equal to drag, the weight is equal to, the thrust is equal to the weight multiplied by the drag divided by the lift coefficient, or 1 over the lift to drag ratio. So if we substitute this into this expression above, we end up with, I realize I've got my head over things. Let me just move myself so I'm less in the way. I'll make myself tiny. Okay, so what we can do now, we can substitute the weight multiplied by 1 over the lift to drag ratio into the equation where thrust was before, and we end up with dt is equal to minus 1 over CT multiplied by G CL on CD multiplied by 1 over the weight dW. So we've got our equation now that can describe for us the incremental time that it takes to go through an incremental weight increment on the right hand side. So we need to integrate this equation, so we need to define some limits. So we'll say the aircraft starts at the at 0 basically. So we'll say we start at time 0 and weight 0. And we'll say the aircraft ends time 1 and weight 1. Now we don't know what these are yet, these are just things we're going to use, but in general this is the aircraft plus fuel, and this one is just the aircraft. So the difference between these two is the fuel, and then the difference between T1 and T0 is the actual endurance of our aircraft. So with that in mind, we can say that the endurance is equal to T1 minus T2, sorry, no it's not, it's T1 minus T0, which is just going to be equal to the integral of dt. So we know that the left-hand side of this equation just yields the endurance. So if we take our equation and we integrate the right-hand side as well, we've got E minus 1 over CTG. I'm just taking all of these constants out of the integral. Okay, so we can integrate the right-hand side now. Our endurance is equal to minus 1 over CTG, CL and CD, and then we have the natural logarithm of W0, sorry, W1 minus W0. So we've got a minus sign in here and we've got a minus sign here. So we'll get rid of those and we'll combine the two natural logarithms using the log laws. So what we've just shown here is the endurance for a jet aircraft. The endurance for a jet aircraft is a function of the thrust-specific fuel consumption, G, which we can't really change. It's a function of the lift-to-drag ratio, and it's a function of this here. So we've got different parameters that we can talk about. If we want to fly for long endurance, then we fly at maximum fuel consumption. Sorry, minimum fuel consumption. So and that sort of makes sense, but again, we like to think about expressions. We think about what they should show us, and this does show us what it should show us, which is that the endurance is inversely proportional to the fuel consumption. We've then got this parameter here, we'll come back to that. This one here is just saying that the endurance is going to be proportional to the amount of fuel. And I'm putting in brackets here, fuel to payload. Fuel to payload or structural weight. So this simply means that a lighter aircraft, in terms of the way that it's made, everything except for the fuel, will fly for a longer period of time. And then this parameter here in the middle is the most important one for us. So we've got here. Okay, I wish that wasn't a brown, I just highlighted that with, let's make it blue. So what this has just shown us is that for a jet aircraft only, the maximum endurance is found at the maximum of CL on CD. And we already know that the maximum endurance, sorry, that the maximum CL on CD is found at the minimum drag speed. So that's found at CL is equal to the square root of CD0 on K, and at VMD, which is equal to B divided by A to the power of a quarter. So for a jet aircraft, our best endurance is found at the minimum drag speed. Now that wasn't what we found for a glider, and it's all because of the way that the effectively, when we develop this equation, it's because we've had to include the thrust in this equation as well. So that's something quite profound. We found that the maximum endurance for a jet aircraft is not the same as for a glider. Now, I mentioned that when we went through the actual development of those expressions, but we've just shown this now. And I'm going to put in brackets here for jet only. Okay, so that gives us the endurance, and that's the condition for which the aircraft can stay in the air the longest. Doesn't necessarily give us, well, it actually doesn't give us the maximum range, so we want to think about how we can determine the range of our aircraft. So if we want to look at the range, we can say that R is equal to the endurance multiplied by the velocity. Common sense, but actually this is only the case if V is constant. So we can't necessarily use this for our purposes. So we're going to define an incremental range. So we say ds, where s is just a displacement, is equal to the formulation that we used for the range earlier, which was the, where is it? Let me go back. So we're going to use this expression here and multiply this by V. So ds for us is equal to minus V divided by Ct G multiplied by Cl divided by CD multiplied by 1 over W dW. So ds is a new parameter we've just come up with. So this is the incremental distance. During a flight for some given speed, which is v. So we need some means of determining what our velocity is, and so we're going to use the good old aircraft speed equation. So we're going to substitute that in there, remembering that v is equal to the square root of 2w divided by rho s cl. So that should just trip off the tongue for you guys now. You should be happy with where that comes from. So we take this and substitute it into here, which is going to give us ds is equal to, let's have a look at this, minus 1 over ct multiplied by g. Then I'm going to put the square root of 2w rho scl multiplied by cl on cd 1 over w dw. So if we look at this expression, we've got CL in the denominator of our big square root. We've got CL here, so we'll combine these two. And you'll notice that I haven't done something. What I haven't done, I haven't taken the weight out of this integral yet, okay? And I'm going to come back to that in a moment. So by take the weight out, I mean I haven't taken this w and combined it with this one yet. And there's a reason for that. And this is one thing that I don't think is particularly well explained in the textbook. So we're going to go through that. But before we get there, we can see that the aerodynamic part of this isn't going to change. No matter what we do with this w, this part's going to stay constant. So what this is telling us the aerodynamic condition, i.e. the velocity, the true airspeed, for the maximum range. So it's the maximum value of CL to the half divided by CD. And I'm going to leave it to you guys to show that the condition that gives this is where CL is equal to the square root of CD naught on 3K. Okay, so that's slightly different. Remember that for our minimum drag speed, it was the square root of CD0 divided by K. This is the square root of CD0 divided by 3K. So it's a lower CL, which means that it's a higher velocity. So our maximum jet range is at a higher speed than the maximum endurance. Now, we can get the speed that we get this at from the good old-fashioned aircraft speed equation. So we'll say V max range is equal to the square root 2W divided by rho S, and this is where we put the CL from CD0 on K. We're going to put this in here, so we get the square root of CD0 divided by 3K. Sorry, I said CD0 on K earlier. And we should be able to see, and it should be apparent to you guys, that that's equal to the square root of 3 multiplied by the minimum drag speed, or 1.32 times the minimum drag speed. So our maximum jet range is at this speed that's always faster than our minimum drag speed, and it's always going to be increased by this ratio here. So I want you guys to be comfortable with this, and I'd like you guys to be able to derive that velocity for yourself. Just make sure you can go through here. If you're not happy showing that this is equal to that, just multiply this out, okay? And you should be able to see that fairly easily. So we've now come up with the actual condition at which our maximum range is going to occur. So we've said that we know the CL, and therefore we know the velocity that our maximum range is going to occur at. So we've still got it in this expression, which is we need to integrate this expression to determine the maximum range. So how we integrate it depends on the sort of climb that we're going to be performing. And let's have a think about what's actually happening on our aircraft. So let's get rid of this iPad a second, get rid of the background. As our aircraft is flying along, it's getting lighter. Okay, aircraft's getting lighter, and as we said, our aircraft weight is in everything. Aircraft weight is a part of all of these performance equations that we've developed. So if our aircraft's getting lighter, then our amount of lift we're producing is getting lower. And if the amount of lift we're producing is getting lower, the CL is also going to fall unless we do something about it. So let's have a think about what we can do here. So as W approaches, as W goes from W0 to W1, our actual dimensional value of lift is going to be getting smaller. So we'll say lift 0 goes towards lift 1, where those two are just the same quantities because we're in a steady cruise. So CL is equal to the square root of 2 multiplied by W divided by rho S V squared. That's just the definition of the lift coefficient. Now we've already said CL for our best cruise, this has got to be constant. So CL has got to be equal to the square root of CD0 divided by 3K. Now for this to be constant, there's part of this that's changing, and it's the W that's changing. So W is getting smaller. So there's two ways that we can keep this constant. Well, there's actually three ways. We could have an aircraft wing that continually got smaller during the cruise, but that's clearly not going to be something we can do. So the two things that we can change is looking at the density or the velocity. So to keep this constant, we can choose to either W divided by V squared can be constant, or W divided by rho can be constant. Those are our two choices. So if W divided by rho is constant, this means that we are at a constant speed. If W divided by V squared is constant, we are at a constant altitude. Okay, if we're at constant altitude, the speed's got to change. And if we're at constant speed, then the aircraft has to change its altitude. And in order for rho to get smaller, the aircraft has to climb. So we've reached what's called the cruise climb. So we've got two conditions that are going to happen for our jet aircraft. For the most efficient cruise, it's either going to have to slow down over the cruise, or it's going to have to climb. And I'll just circle the climb there. So those are the two things that are going to happen on our aircraft. So let's develop these. We'll develop these slightly differently for each of them. I'm going to develop the constant altitude first. So let's go over here. So for our constant altitude cruise, let's go back to our expression. I'm going to rewrite it. We'll say that ds is equal to minus 1 over thrust specific fuel consumption, acceleration due to gravity, 2 times W over rho S CL to the half divided by CD 1 over W dW. Okay, so in this case where we're looking at constant altitude, then because we've already described the velocity in terms of the lift coefficient, we have to take W and we have to put it into the right hand side of the equation now. Sorry, not the right hand side of the equation, it's already in the right hand side of the equation. We're going to take W and we're going to combine it with this one here. So we end up with minus 1 over CT G square root of 2 divided by rho S CL to the half divided by CD, and what we would have here is W to the half divided by W. That's the same as W to the 1 over W to the half. So we've now got an expression that we can integrate. So let's do this. Let's say the integral from S0, or from S1 to S0, is going to be equal to the integral on this side, W1 to W0. Now actually I've written S1 and S0 here. I could have just written R and 0 there. Okay, so this gives us the range on the left hand side. So let's say the range is equal to minus 1 divided by CT G. I've got the square root of 2 divided by rho S multiplied by CL to the half divided by CT, and then I'm going to have 2 W1 to the half minus 2 W0 to the half. Okay, and I can just tidy this up a little bit. I'm going to say that my range is equal to, I've got a minus sign here and I've got a minus sign here. So let's just flip the terms in the brackets and we'll write it as a positive quantity. I'm also going to take the 2 out of the brackets and put it into the square roots. Okay, and when you go through this, if you're driving it, which you need to go through, remember that range needs to be a positive quantity. An aircraft can't have a negative range, and this is the W0 is the end weight. W1 is the end weight. W0 is the starting weight. So this gives us the correct signs in our. I've just made my own mistake there, and I've realised I've tried to talk about how we know we got this right, and I've made a stupid mistake here. W1 is the end weight. W0 is the starting weight. So this would be a negative quantity. I said I'd flip these two things round and I haven't, so let's just change those two round. I flipped them round because I got rid of the minus sign at the beginning. So let's just get rid of those. I like to keep my mistakes in because it shows that I'm a human being and it shows you guys how you should know when you make a mistake. Okay, so what we've now just determined, this is the range for the constant altitude. And for that, we know therefore the speed has to change. So the speed, not the feed, falls. The speed falls with the cruise, meaning that our aircraft is going to slow down as we go along. Okay, so this altitude in here is going to be a constant, and everything else in here we can determine. So we've got the thrust specific fuel consumption, we've got the acceleration due to gravity, we've got the density at whatever altitude the cruise is occurring at, wing area, CL, which we have said is going to be given by CL is equal to the square root CD0 on 3K. The drag, well, what's the drag going to be? CD is equal to CD0 plus K, and it would be CL squared. So we're going to take this, substitute it in there, get rid of the square root, we get CD0 on 3K. So we get, hidden behind my head, we get 4 CD0. Okay, there we go. 4 CD0 is the drag for those. So we take our CL, take our CL, take the square root of it, divide it by this quantity here, and we put those in there. And then these are just function of the aircraft and the amount of fuel it's got. And this will give us the aircraft range. And we'll go through some numerical examples. Or in fact, I might just put them up on the website and you guys can go through those. So that's the constant altitude cruise. Let's have a look at the cruise climb now. So what's occurring in the cruise climb case? Let's have a look at the equation we've got. So our incremental distance is equal to minus 1 divided by CT G multiplied by 2W divided by rho S multiplied by CL to the half divided by CD multiplied by 1 over W dW. So if the aircraft altitude's increasing because we're trying to maintain this constant speed, then in order for that to happen, W divided by rho remains constant. So if W divided by rho is constant, then this is no longer part of the integral expression. So we then can just simply use the ratio between those two at the start of the cruise and include them in our parameter now. So include them in our equation. So we'll call this W naught divided by rho naught. And importantly, this is wherever we start the cruise at. Because we know that as soon as we start burning fuel, the aircraft gets lighter and it's going to climb in order to keep this equation holding true. So this is equal to minus 1 over CT multiplied by G, and we keep all of these terms in our expression now. So we've got square root of 2 W naught divided by rho naught S CL to the half on CD. And in fact, let's just go straight through and do the integral, because this is exactly the same as we did for the expression before. So I'm going to get rid of my minus sign here. If I can get the right eraser working. And we can then say this is the natural logarithm of W naught on W1. Okay, so again, we've got the exact same CL and CD. So the exact same CL and CD that we flew the constant altitude cruise. For the cruise climb case, which is the constant speed, we use the same CL and CD as before, and we've simply got to include a couple of other parameters. So remember, we've got the start weight, and here we've got the starting density, or the density at the start of the cruise. So it's important to note again, the range here is inversely proportional to the density, or the square root of the density, so we'll get a further cruise, or a better range, if we start our cruise at a higher altitude, and that sort of makes sense for this aircraft. So how do we determine actually what our numerical range is for either of these? Well, it's exactly the same. We know the CL and CD for each of these. We know that it's going to be the CL is equal to the square root of CD0 divided by 3K. CD is going to be equal to 4 multiplied by CD0, and then it's just a case of substituting values into either of these equations here. It's not particularly taxing, so I've put an example up on the website. Now let's just link into that. This isn't live yet, but it will be by the time this lecture goes out. So let's just copy into here. Now again, this question is going to be slightly better formatted by the time I go through it, by the time it's ready. So I'm asking you to look at a question that's been adapted from something in Anderson. Anderson's is aircraft performance and design. So it's adapted from his. I've slightly changed the numbers, and I've changed what I'm asking you for in this question. But I've then gone through a full example of how it's calculated, and importantly, I've done it in both US customary and SI units. Now, my class knows my ill will towards US customary units, and I think it's probably shared by most of the class because you're all under 60. But I've gone through, and what this does is then for those different altitudes, calculates the constant altitude range and the cruise climb range. And in all cases, we'll see the cruise climb gives us a better range, okay? What I'm also doing there is I'm calculating a couple of other parameters. So in the cruise climb range, I'm seeing how much the aircraft climbs. Okay, so have a look at those and see if you can determine how I've calculated the increase in altitude. And the same for the constant altitude. I've determined the starting speed and the end speed of those two cruises. I think I've included them there. I have included them on there. That's good. Okay, so those are all included on the website, and I want you guys to go through those and understand them, because you will be asked to do calculations like this. So if there are questions about the Breguet range equation and how we actually apply it, then I need you guys to ask questions, come with those, go through it, and come to the review session such that we can go through it. Okay, so where are we at? Okay, so we've gone through propeller aircraft. Now I'm just showing you we've gone through jet aircraft. We haven't done propeller aircraft yet, so we're going to do the same thing for propeller aircraft now. Okay, what about props? Well, anyone who's been to my office and seen the titanium propeller blades that I like to use as sort of pointing sticks knows that I've got an affinity for props, only because I like their aerodynamics. In terms of performance, they're interesting, but we're going to talk about them now. So how do we develop the Breakaway range equation to determine endurance and range for props? So we have the exact same starting condition, which is the rate at which the aircraft weight is reduced is equal to the rate at which the weight of fuel is burned. So our starting thing is again dW on dt is equal to minus. Now here we have the specific fuel consumption, and we've got to multiply that by the power that's being produced by the engine, and then we multiply that by G again. So we've got to be careful here. Power is not, in this case, dV, because what dV, that's the power that is required to push the aircraft forward. the power that's being produced is always going to be slightly more than that because of the efficiency of our propeller. So we say that the power is equal to drag divided by the velocity, drag multiplied by velocity, divided by a quantity called the propulsive efficiency, or we'll say this is the combined propulsive efficiency. Now this is a number that's always less than 1, and what this term here combines, this combines the fact that a propeller or any form of engine whereby we're accelerating a mass of air doesn't gain anything by giving the air kinetic energy. We only gain thrust from giving the air momentum. Okay, so there's part of that in there. There's a fluid dynamic problem where there's a maximum theoretical efficiency, and also engines produce a lot of heat. Engines produce a lot of noise as well, and all of those are doing work that don't help us. So we combine those efficiencies together into this combined propulsive efficiency, and you'll be told this if we need to go through a question for propeller efficiency. So we can then substitute that into our equation. So dW divided by dt is equal to minus c, and then we just substitute that into here. So I'm going to change, excuse me, g multiplied by dv divided by eta. And then again we'll rearrange for dt. It's equal to minus eta divided by c g multiplied by dv. Again, then I've got a dw in here. So this is our integral expression here. Just as before, we're going to do something funky with the drag. We're going to say the drag is equal to our drag multiplied by our weight divided by our lift. So that's equal to, in our case, the aircraft weight multiplied by CD divided by CL. So then we can just make that substitution. We'll say that dt is equal to minus eta divided by c g v, and then what have we got now? We've got CL on CD 1 over w dw. Okay, so if we want to integrate this expression, this is going to give us the endurance of our aircraft if v is constant. So we're going to assume constant velocity. And then if we integrate the left-hand side, our endurance is given by minus eta divided by c g v CL on CD. And then in fact I'm going to again skip the integral step here. I'm just going to make this the natural logarithm W0 divided by W1, just because we've done all of this already before with the exact same expression. So our endurance is given by this expression for our propeller-driven aircraft. So what we've actually got to maximize is not CL on CD, it's this term here. So our maximum endurance at the maximum value of CL divided by V on CD. Okay, so if you want to work out the velocity at which that occurs at, you can go through and you can follow the exact same method to maximize this, or you can represent the velocity using the aircraft speed equation. So if we wanted to find the maximum of this, yeah, that's one way we could do it. We could say V is equal to 2W divided by rho SCL. Substitute that in, get a dirty expression in looking at what we got to manipulate. And you'll end up showing the minimum power speed. So let's just be a little smarter with this. Let's say that if we want to maximize this, we can say V CL and CD is equal to V. Sorry, that's not V CL CD. It's CL divided by V CD is equal to the lift divided by VD, which is equal to the lift divided by the power. Okay, and this is the power required in this case. So the maximum quantity there is going to be at the minimum power required. So hence max E at VMP. Okay, and we've already determined the speed that is. So we know that's at the minimum power speed, so we can get that and we can compare that for a propeller driven aircraft. If we want to find the range now for our aircraft, for our propeller driven aircraft, then we should easily be able to see actually that we've already assumed constant speed, which is just a simplification we're making for our propeller aircraft. We can see if we take this expression and multiply it by V, we're simply going to get rid of the V here. So let's just, you can still see that up there. Let's come down here. Okay, so this is something really important. We've just shown that our range of our propeller driven aircraft is given at the maximum value of CL on CD, which we know occurs at the minimum drag speed already. So we know that, we've shown that, we know max CL on CD occurs at VMD. And we know that the maximum value of the, so we've got these two quantities here, VMD is simply B on A to the quarter. VMP is B on 3A. I think that's correct. Let me just check. I'm always slightly worried when I put these up from memory. The minimum power speed, I'm pretty certain is B on 3A to the quarter, but I just want to confirm. Yes, minimum power speed B on 3A. Okay, so our maximum endurance is given at B on 3A, maximum range is given at B on A. We can show something else here with the endurance here. If we substitute the aircraft speed equation in here, you can see endurance is equal to eta divided by C, G, and then I'm going to have to do 1 over the aircraft speed equation, so that's going to be rho SCL on 2W CL on CD here. So what we've just shown here is actually that the endurance is proportional to, well, it's proportional to the square root of the density, but this shows us here that for max E, we've got to fly at sea level if we're in a propeller driven aircraft. So endurance gets better for, well, the endurance gets better the closer we are to the ground with a propeller driven aircraft. Okay, and then we see here actually the range is then not a function of the altitude at all. Okay, so for a propeller driven aircraft the density doesn't appear in here at all. So we can just summarize those parameters that we've gone through, and I'm going to talk about this and hopefully put some fancy overlaid titles on instead, because I think sometimes if I can speak directly to the camera things look a little bit better. So we've gone through a few things today. We've defined what range is. Okay, so 3 different sorts of range: range, still air range, gross still air range. And we said that one, gross still air range, is the one that we're going to calculate. We developed the Breguet range equation, which can be distilled down to thinking about the rate at which the aircraft weight reduces is the same as the weight of fuel that's being burned. And we then showed a few things. We showed that if you're in a jet aircraft, if you want in fact, let's talk about them all. So for a glider, we showed this already. We showed that our maximum endurance was at the minimum power rates. For a jet aircraft, maximum endurance is at the minimum drag speed instead. And if we're in a propeller aircraft, our maximum endurance is at the minimum power speed again. Range is slightly different. So range for a glider is found at the minimum drag speed, and it's the same for a propeller aircraft, found at the minimum drag speed. For a jet aircraft, this is at some speed that's greater than the minimum drag speed, and it's that proportion 1.32. Okay, so there's some numerical examples online. I'd like you guys to go through them, make sure you can understand them, because we are going to be giving you, well, I will be giving you questions on this in both your module 3 tests, or in your week 3 quiz, but also in your take-home assignment. You're going to have to do these calculations for an aircraft of your own. So thank you for tuning in today, for listening to me. If there's any questions, pop them on Slack, put a question in the comments or whatever, and I will see you all in the next lecture. Thank you.